All right, I'm starting neurotransmission. You're going to see that this is highlighted. This is take 2. My phone fell off of my little lamp extension here. The tape didn't hold, and so that's why you're seeing it highlighted. Okay, I'm going to do the very best I can to repeat everything I just said to you a moment ago without going too quickly. So, nervous transmissions can occur electrically and chemically. Okay, nerve impulses are when a neuron's threshold value is reached. So we know we've seen electrical stimulation in terms of the action potential. Today I'm going to talk to you about chemical transmission, and that's called neurotransmission. So most neurons interact between a synapse. Okay, the synapse is the distance or the space between the axon of one neuron and the dendrite of another. So when the nerve impulse arrives at the synapse, it may cause the release of a neurotransmitter. Okay, in many cases it will cause the release of this neurotransmitter. The postsynaptic neuron can receive impulses which are both excitatory and inhibitory. Okay, so at the end of the neuron, the postsynaptic neuron, the one that's coming next, can receive impulses which are excitatory and inhibitory. And so what the next neuron does is it takes a sum total. I find that amazing. So it totals how much excitation is being sent to it and how much inhibition is being sent to it, and it does the math. And if the sum is excitatory, so positive, it's going to send the message. And if it's inhibitory, the message is never going to get sent. So if the sum is inhibitory, the neuron is less likely to fire. Okay, and so what I drew here is I drew an action potential, and then I just said if we don't get past this point, okay, then we're not going to have the action potential. And so the neuron is not going to fire. It's very unlikely to fire if it can't get up beyond that threshold value. All right, and how do we get beyond the threshold value? The neuron takes the sum of excitation and inhibition coming from the neuron before it to decide if it's actually going to send its message off. Very cool. So an action potential is all or nothing, and that's what I was showing here. If we can't get past this, this is not going to happen. The action potential is not happening. Once the action potential is initiated, it will lead to the release of a neurotransmitter, likely, okay? In many cases it will. And so you don't know what a neurotransmitter is yet, and that's my job today to tell you what a neurotransmitter is. So a neurotransmitter is a chemical made by the nervous system, okay? So it's made by the nervous system. It's not made by the endocrine system, okay, which would be hormones. This is something entirely different. And so what I'm going to do is take you through the stages in neurotransmission, and then we're going to look at them on a diagram. So if you don't get it on the first run, it's okay, because then we're going to look at the diagram like we would if we were in class. So background notes. The first thing we have to do if we're going to send a chemical from one neuron to the next. So why would we do this? Because it helps to tell the next neuron that there's something going on, okay, that it needs to fire. So if you're wondering, how does the message go from one neuron to the next? This is the answer to your question. In many cases, it's going to be because of a chemical. So first of all, we have to make the chemical, all right? So stage 1 in neurotransmission is synthesizing the neurotransmitter. That can happen in many different places depending on the type of neuron you have. So it can happen in the cell body, the axon, or the axon terminal. Then what we're going to do is store the terminal, or store the neurotransmitter until we need it, okay? So let's make it, and then let's store it. And so this is what your neurons do as they're newly made. They make neurotransmitters, and then they store them in vesicles. So you know what a vesicle is, right? It's a membrane-bound organelle. It looks like a vacuole. A vacuole is a form of a vesicle. A lysosome is a form of a vesicle. So the storage of neurotransmitters in vesicles, and it's stored in the axon terminal. So these guys are going to be stored in the axon. Now, calcium enters the axon terminal. That's stage 3 here. So calcium enters the axon after we have an action potential, during the action potential, and it causes the release of the neurotransmitter into the synaptic cleft. So that's a lot to take in one sentence. So what I want you to know is calcium will enter the axon during an action potential. We allow calcium to enter via protein channels that are specific to calcium, and calcium binds to the vesicle. Okay, so calcium binds to these vesicles, which allows for the release of the neurotransmitter. Okay, so if you have nervous twitches, like not nervous twitches, muscle twitches. You know, sometimes the nerve in your eye starts to go. Oftentimes it can be, oftentimes, not always, it can be a lack of blood calcium. And so this is where, again, that the endocrine system plays a part, because if you don't have enough calcium in your blood, then PTH is going to take that from the bones, right? So what you need to do is make sure that you've got a good source of calcium. You need to up your calcium levels if you're getting little twitches, because this is one of the reasons, all right? You're not sending your messages efficiently. And so calcium is definitely involved in nervous transmission. The neurotransmitter binds to and activates receptors in the postsynaptic membrane, and that's where I was when my phone fell off. So I was drawing a really bad diagram of a neuron. Okay, so those are the dendrites coming into the cell body. Here's our axon, okay, and then here's our next cell body with its own axon, and here are the dendrites coming off, okay? And so you can see there's pretty close contact, not completely close contact, but if this is the axon and this is the dendrite, okay, what you need to know is the neurotransmitter is traveling through and it's binding to the postsynaptic membrane. Okay, so it's coming from the postsynaptic membrane and then it's going to go in this direction. So right here, moving forward in that direction. So this is the postsynaptic membrane here, and this is the synapse, okay? And this will be the membrane of the next neuron. So we would see this is the next neuron. Postsynaptic membrane, okay? Oh, sorry, I'm saying that completely incorrectly. The postsynaptic membrane is going to be here, okay? Because it's past the neuron. All right, it's past the synapse. So this is the presynaptic membrane. Okay, this is pre, sorry to confuse you. That's pre and that's post, because this is our synapse, this space here, okay? So the neurotransmitter binds to and activates receptors on the postsynaptic membrane. Again, if it's not making a lot of sense, it's going to in a couple minutes, hopefully. And then once the effects are felt by this neuron here, so we'll call this neuron A and neuron B. Once neuron B gets the message and it knows that it has to fire, it's going to fire because of the neurotransmitter that it's received, then we can get rid of the neurotransmitter. Because if we don't get rid of the neurotransmitter, we're going to get an amplified response, okay? This thing is going to be amplified and it's going to be firing like crazy, okay? And you don't want that in any case. So what I'm going to do for you, get you to do for homework, because I'm drawing this week, we're going to go a little bit more slowly this week, and I haven't overloaded you with work, so that hopefully you can catch up. What I want you to do is read about the effects of illegal drugs, okay? So I know that sounds terrible, but I want you to really, really read about what cocaine does, what marijuana does. I'll get into that a little bit. I know marijuana is not illegal anymore, but what it does to these responses here, okay? And so I think you're going to be interested in that, and I just want you to know what the effects are of these drugs. So if we don't take that drug, if that neurotransmitter doesn't get taken back, then we're going to get an amplified response, and we don't want that, okay? So our bodies know when to say it's enough. So we get a deactivation of their neurotransmitter in one of two ways, and I'll go through this again in a little bit. Either you're going to recycle that neurotransmitter, and it's called reuptake, okay? So in other words, I'm sorry this diagram is so small, but in other words, if there's a neurotransmitter in this synapse, then and I'll show you this very clearly on the diagram that we're going to be looking at, this takes back the neurotransmitter, okay? So the presynaptic membrane takes back the neurotransmitter and keeps it for the next time it has to send it out. So that's called reuptake, all right? So reuptake happens when you take it back into the terminal from which it came. The other alternative is we can take it apart, okay? Reuptake is clearly more efficient, but not all of our systems will work that way. Not all of our neurons work that way. So sometimes this is just going to get deactivated, which means you're going to pull it apart, right? You're going to take the different structures apart, and it's not going to be working anymore. So neurotransmitters usually bind and stimulate their receptors, then travel back to their sending neuron. That's called reuptake, okay? Usually do that. Reuptake occurs in order to keep the neurotransmitters levels steady and maintain homeostasis. So reuptake maintains homeostasis. And this is what I said to you. The receiving neuron, so the one on the postsynaptic, the one that has the postsynaptic membrane where the dendrites are, basically says that's enough. I've had enough of the neurotransmitter, I get the message, and take back the neurotransmitter. Some disorders occur, and I'll probably get to that today. Some disorders occur when we don't know when to say that's enough. Okay, so and as I go through these different neurotransmitters in a moment, you'll understand that a little bit better. Okay, so if your neurotransmitters are functioning properly and you don't have any real mental illness, for instance, then you're saying that's enough at a good homeostatic level. Okay, many people's neurons don't know when to say that's enough, and that's what we call a chemical imbalance. All right, and so you need a little bit of help in the reuptake process. So I'm going to get to these different neurotransmitters in a minute. What I would like to do with you is go through this diagram on 25C. Okay, so this is an awesome diagram, and it really goes through everything I just said to you. Okay, and I always find, and I told you this before, I think we can learn better with diagrams. So what we're seeing here, okay, so let's start with one. The transmitter is synthesized and then stored in vesicles. Okay, so I'm going to color the transmitter in the neurotransmitter in pink. Okay, so we're just going to color code here like usual, and I'm going to color code that in pink. So your neurotransmitters are made. So step one, like I said, you've got to make the neurotransmitter, and then what do? You store it in this vesicle, okay, for whenever you need it. So that's step one. Okay, it's being stored. Step two is the action potential invades the postsynaptic terminal, the presynaptic terminal. So in other words, action. Okay, we've got that action potential coming around. What does that mean? We've got this is all going to be depolarized. So depolarization is happening. Now we're in the tip of the axon. If you're trying to picture where you are, you're in the very tip of the axon. Okay, so we've taken care of that. Depolarization of the presynaptic terminal causes the opening of voltage-gated calcium channels. So this is where calcium comes into play. I know it's a really small little protein channel, but this is your Ca2, okay? And I don't see my pencil case on my island right now, so I'm not going to highlight it, but I might have highlighted that in blue. Okay, so calcium is now, as soon as that action potential comes through and this membrane becomes depolarized, okay, so depolarized in this area, then what we do is we allow calcium to come in. Okay, so I've got little calcium and tiny little blue dots there. Okay, Ca2 positive. This is where calcium plays a role in transmission and why we have to maintain a certain level of calcium in our blood. Okay, so what calcium does then is it binds to the neurotransmitter vesicle. Okay, so there are going to be little receptors on here for calcium. All right, just like lock and key, enzymes, all of those things that are specific. Same thing is going to happen here. So number 5, calcium causes vesicles to fuse with the presynaptic membrane. So when calcium binds to that, it doesn't tell you that it's binding to these receptors. There are receptors there, but that's essentially what's happening. So the diagram is just missing that. And so we would have calcium here. And so as soon as that happens, what calcium does, because of the binding to the vesicle, is it tells that vesicle chemically, you're going to release this neurotransmitter. And so the vesicle then moves down to the presynaptic membrane, okay? And so what happens then is the vesicle opens up and you get the release of the neurotransmitter. Now, what is this? This is the synapse, okay? So right in here, this is our synapse. Okay, I hope you're following me so far. And so this is another vesicle, okay? And then we're going to have, in time, this could be the same vesicle. They're showing us an arrow. So they're saying this is the same vesicle. And the vesicle is just releasing its neurotransmitter into the synapse, okay? Now, this is the next neuron, okay? So this is the dendrite, and it even says that across dendrite, okay? So this is your next neuron. This is the presynaptic membrane. This is the postsynaptic membrane. And the postsynaptic membrane belongs to, as I said before, this is neuron A, and this is neuron B. Okay, so this belongs to neuron B. And what happens, I'm sorry if I'm making it very complicated, I don't mean to. What happens is you've got these neurotransmitter channels, okay? So what they do is, number one, the neurotransmitter binds to these channels, okay? And what it does is it says, okay, so let's go through here. Transmitters released into synaptic clefts via exocytosis, good, okay. And then 7, transmitter binds to the receptor molecules in the postsynaptic membrane. So here's our postsynaptic membrane all in here. Okay, I'm sorry if I'm coloring it the same color as the neurotransmitter. And then number 8 is the opening or closing of the postsynaptic channels, okay? So in other words, what happens is that you get the ions coming in, okay, or you get the neurotransmitter coming in, and it says we are going to have an action potential. So this says, okay, there's an action potential happening here in this neuron A. You have to decide, neuron B, if you're going to respond and send it further, all right? And so because the neurotransmitter is activating and it's going through these transmitter channels, then it's probably going to respond and send that message forward. Now, when the message is sent and this neuron says, okay, I've got the message, cool it, right? I'm done. So then what happens is that we get, and they're not showing it here, in many cases, the neurotransmitter is going to get taken back up. And that's called reuptake, okay? So this neurotransmitter is going to get collected and taken back up. If not, they're showing you in this diagram that the neurotransmitter is going to get destroyed. So they're showing it going this way, and then you would not have the neurotransmitter anymore. Okay? So you can now repeat that if you need to have it repeated over and over again, as many times as you need. That is how neurotransmitters work. Okay? So what I'm going to do finally, I know it's a long lesson, but you can certainly shut me off whenever you want to. I'm going to go through specific neurotransmitters with you, okay? So this is where things get a bit more interesting for you guys, all right? So here are a few examples of specific neurotransmitters. So we've got serotonin, okay? So serotonin contributes to feelings of wellness and happiness, all right? So serotonin makes you feel really happy. It plays a role in reward. Okay, so a role in reward. So if you do something over and over again and it makes you happy and feel good and you get a benefit, you're releasing serotonin every time, and your body really likes serotonin. And so what it does is it says, okay, I'm going to do that again tomorrow because I liked how I felt after. All right? Serotonin plays a role in learning, okay? So it plays a role in learning because if you're learning that you're going to make serotonin to get a reward, your reward is serotonin, then you're going to learn how to get that serotonin again, and you're going to store that memory, okay? So these are the things that serotonin plays a role in. Serotonin, this is where it might have come from in terms of evolution. It says it's transported in platelets to initiate blood clotting. So serotonin is transported in your platelets, and that initiates blood clotting. So you're going to have an overall feeling of wellness if you're clotting your blood and stopping a lot of blood loss, okay? And so this could be, I think maybe in some cases, the origin of where serotonin, how we start to have feelings of wellness, or it definitely has to contribute. Because if you're clotting your blood, you're losing your blood, and so you are healing, and therefore you are going to be well, okay? And serotonin is made chiefly by the liver. I won't highlight that. So that is one of the neurotransmitters that can be released here, okay? And that's going to trigger the feeling of wellness. Now, here's where I said that that's enough comes into place. So Prozac and other antidepressants prevent the normal reuptake of serotonin, okay? So if you are depressed, in a state of depression, it's been studied that you are not releasing enough serotonin, so that neurotransmitter is a little bit low. And so what Prozac does is it prevents the reuptake of serotonin. So if serotonin is pink, that means you're going to let serotonin sit here longer. We're going to take more serotonin in, and so we're going to feel better, okay? So Prozac doesn't allow the reuptake to happen as quickly, okay? And not as much is taken back in, because people that are going through depression need more serotonin in that area, okay? So I hope that explains a little bit to you, because we probably all know somebody that is on antidepressants, okay? Today's world is a crazy world, and because we're going so quickly, and now even with COVID-19, there's a lot of need for antidepressants. So Prozac and other antidepressants prevent the normal reuptake of serotonin, leading to an increased stimulation of serotonin in the neurons and in depressed people. Just a fun fact, chocolate may increase serotonin production in the gut, okay? And that should say, and help the immune system and increase serotonin in the brain. So you might think that that effect that you have with chocolate is, it's also a sugar high too, right? Because the more sugar we get, the more dopamine we produce and the happier we are. But it is believed that chocolate may increase serotonin, may increase it. I believe it, but not everybody does. Okay, so another neurotransmitter called noradrenaline and norepinephrine. You've seen this before when we talked about the endocrine system. Noradrenaline regulates arousal. Okay, it regulates dreaming. So when you're sleeping, it's very, very low. You've got low levels of noradrenaline, and that causes you to dream. And it definitely has an influence on your mood. So noradrenaline increases blood pressure and heart rate, and these are stress responses, okay? So if you need to act on something, it's going to do this. It's going to increase your blood pressure and your heart rate. And so lots of noradrenaline increases your stress response. Low noradrenaline increases your relaxation, all right? So what does noradrenaline do? It promotes attention and alertness. It is used for patients with low blood pressure. So these guys are in use. These neurotransmitters are used frequently. And then interesting here, if you've ever heard of beta blockers, okay, beta blockers block the receptive sites for noradrenaline, norepinephrine, and are used for patients with high blood pressure. Remember, this is increasing your blood pressure. So if your blood pressure is already too high, then they give you a medicine, and I'm sure you guys have heard of it, called the beta blocker. And the beta blocker blocks receptors for norepinephrine or noradrenaline, okay? And therefore, it's going to help you reduce your blood pressure, all right? Also used in eye drops for glaucoma. Glaucoma is a condition where you have high pressure in the eye, and it can lead to blindness, all right? So if they can reduce the pressure in the eye, then they can maintain that health of the eye longer. And norepinephrine is banned by the International Olympic Committee because of its effects in reducing anxiety. So some people get too stressed and they have performance anxiety. And so now the blood is tested to make sure that everybody's on an equal playing field and they're not taking extra noradrenaline, okay? All right, dopamine plays a role in reinforcement and reward more than serotonin does, okay? So also plays a role in motor control and motivation. So your motivation to get reward. Now remember, serotonin is an overall feeling of wellness and happiness. Dopamine is a little bit more aggressive in the fact that it's trying to get you to do something to be rewarded. Okay? So you're going to be motivated to get your reward. So it has a role in causing wanting and pleasure related cognition. What does that mean? Cognition refers to learning. Okay? So your brain is wired to learn what makes you and your body happy. So if there's some kind of reward that you really want, guaranteed your brain's going to learn about that, okay? So it says neurons containing dopamine are clustered in the substantia nigra. We're going to get to that in the midbrain and the retina, and in the retina. In Parkinson's disease, dopamine transmitting neurons die, and thus the body has muscle rigidity, tremors, and changes in speech. Remember I said to you that dopamine is involved in motor control, okay? So if we decrease dopamine, we decrease our motor control, and you're going to see that in Parkinson's, okay? So there's low dopamine in Parkinson's. So dopamine transmitting neurons die. High levels of dopamine increase the activity of cone cells, okay? And low levels lead to the activity of rod cells. So cone cells are active during the day. So we say this is our vision in light. So if you've got lots of light, I'm saying day because during the day you've got lots of light, and your rod cells are more active at night. It's not that they're not active during the day, but they are way more active in low light at night. Okay, so these guys help you to see your color. We have color vision. Now at night your color vision gets very skewed. These guys help you to see black and white. Okay, cone cells offer great clarity. So right now, if you're looking at a piece of paper, you can see the edges. If you were to look at this paper at night, the edges are going to become fuzzy. So just something that you might want to take with you. So cone cells are active during the daylight, and they show you your colors, and they show you really distinct images. These guys are exactly opposite of all of that. So high levels of dopamine lead to activity of cone cells. So in other words, when we're awake during the day and we're in a great deal of light, our dopamine levels are going to be high because they're firing to the eye. All addictive drugs influence dopamine levels. Okay, so I'm not going to keep you much longer. That is neurotransmitters. We've gone through this. Okay, read through 25C at the bottom. Okay, over here, you guys can read this just as well as I can, and you're going to be definitely tuning my voice out at this point. So read through this, okay? It's extremely interesting. Dopamine, increased levels associated with schizophrenia. If you're interested in that, you can certainly investigate that further. Cocaine elevates dopamine levels, and amphetamines elevate dopamine levels, okay? So that's something I want you to be aware of. And then I'm getting you to read a little bit more about drugs and what they do. Okay, I won't spend the time here, unfortunately, but if you want to look up marijuana and the active ingredient THC, please do that, okay? Understand what it does to you. It certainly does influence your short-term memory. It influences your muscle coordination. You are learning, even though you think you're on to amazing discoveries, that's not actually happening, and problem solving, okay? So it has adverse effects on those things, all right? So just be aware of that. And then it also affects whether you want to eat or not, all right? So that's all in here. Usually I spend the time and go over this, but I won't this semester. I want to point out just maybe one or two more things here. Endorphins are those natural painkillers that we have. It's a neurotransmitter. When you're running, you would actually feel quite a bit of pain. I think I might have said that already. The compression of the muscles and the joints and everything running and hitting the ground would actually not be a great feeling. So because it's so good for our cardiovascular system, so good for our heart, what we do is release these endorphins, okay? And when you're done the run, you still have a lot of endorphins left. You haven't done the reuptake yet, and so you get your runner's high, okay? And there's something with reward. After you run, you might not feel like starting the run every day, but you know at the end of it how awesome you're going to feel. And so that is part of reward, okay? Releasing these endorphins, you know you want to run again because you felt so awesome the day before, okay? Opiate drugs can be involved in that, so they mimic endorphins, and I think I'm going to leave it there, okay? So please look up, I've got a note on cocaine and a few other drugs. Do understand that, and what I want you to just understand, just as I wrap this up, is what cocaine does is the very first time you take it, it makes you release lots and lots of dopamine, okay? And so on the very first time, I hope you never take it, so I shouldn't say when you take it, when a person takes it, they release a lot of dopamine. And so they get this extreme high from the dopamine. And then again, if you want to go back and see what dopamine does, you can see that. And then so it's pleasure, right? Dopamine is pleasure. So it's there, right? It's already on this page for you. So when the next time they do it, the dopamine is not going to be as readily accessible because once you take cocaine, once a person takes cocaine, it mimics the effects of dopamine, and then you start to make less dopamine. So the brain goes, I'm not making as much dopamine because I don't need to, because this drug is going to provide me with that, okay? And so the point is this, on the very first time that a person takes cocaine, they get this intense high, and then every time they take cocaine thereafter, they want to reach that high, but they can never reach that high again. Okay, because your body compensates by making less and less and less dopamine, and then you have to take more and more and more cocaine to feel those effects. All right, so I just thought I'd share that with you. All right, have a great weekend, guys.